All right, so we've talked about velocity and speed already, but I want to review it just briefly because we're going to talk today about position versus time graphs, and you have to know a little bit about velocity to understand it. So we'll talk about velocity, speed, and then I'm briefly going to talk about acceleration, and then we'll look at position time graphs. So here's the definition for velocity. Velocity is defined as change in position. Change in position. So this delta right here is change. The x represents position. What's another name for change in position? Displacement. Delta x is referred to as displacement. And change is always final minus initial. So you're going to go position final minus position initial. For change in time, you would go time final minus time initial. Now, what is the unit that we're going to be using in physics for velocity? So in everyday life, we talk about velocity or speed in miles per hour. That's the most common unit we use. But in physics, we don't want to be in miles. We want to be in meters. So these positions, like in yesterday's lab, you guys marked your positions. You went outside with a little piece of chalk and you marked the 0 meter position, 5 meter, 10 meter, 15 meter. So we measure our lengths in meter and we measure our times in seconds. So this is the unit for velocity. And same thing for speed. If you're dealing with speed, you're going to want your distance to be in meters and your time to be in second. Those are the metric units for velocity and speed. Okay, so let's see what else about this. Let's talk about acceleration now. Okay, so acceleration, you all have an idea of what acceleration is. You know, when you're sitting at a stoplight at rest, the light turns green, you put your foot on the gas pedal, and you accelerate. So in acceleration, all it is when an object has a change in velocity. You know, if you go from 0 velocity to a velocity of 3 meters per second, that's a change in velocity. Now, how does time factor into this? Well, if you look at this equation, acceleration is change in velocity over time. The quicker you change your velocity, so in other words, as delta t here becomes smaller. If you change your velocity quickly, that means the delta t is going to be smaller. What happens to acceleration? If you're able to change your velocity quickly, then you're going to have an acceleration that's what? Big or small? Bigger. You know, as the denominator here, as this denominator gets smaller, as time gets smaller, acceleration gets bigger. So acceleration is change in velocity per time. So what unit are we going to get for this? And notice, you know, change again is final minus initial. So what's the unit for velocity? Meters per second. And then what's the unit for time? Seconds. So we get this very odd looking unit, you know, which at first it's kind of hard to get your brain around it, at least for most kids. The way you're going to see this on worksheets and in the textbook, you're going to see the unit for acceleration. What would that simplify to? Meter per second over second is the same as what? Meters per second squared. And this is highly confusing. Like what is a second squared? How do you take, like if you took 1 second on your stopwatch, you timed something that took 1 second, what would the meaning of that second if you squared it? Can you wrap your head around that at all? I can't. So what I want you guys to do is you're going to see the unit for acceleration this way. It's going to be given as meter per second squared, but what is meter per second squared? It's really meter per second per second. So what is meter per second per second? So here's an example. So let's say that t initial is 0, right? Like you're standing there with the stopwatch and the stopwatch says 0. And let's say the initial velocity of the car is 0. So just like you were doing the walk lab yesterday, you're at the beginning of your course, the stopwatch says 0, and you have a velocity of 0. Let's say that this car accelerates at 2 meter per second squared. Uh-oh. Uh-oh. Two meter per second squared. So that's going to be the acceleration for the car in this little example. What does 2 meter per second squared mean? It means 2 meter per second every second. So if this is 1 second, right here, so over here this is t equals 0, right here is t equals 1. If the car has an acceleration of 2 meter per second squared, that's 2 meter per second, what will be the velocity at t equals 2? I'm sorry, at t equals 1, right here. What would be this velocity? 2. Okay, so now let's draw the car in over here. So in fact, I'm not going to use this building right now. We'll do this building later. So let's say that right here is the car. Let's say here's the car at t equals 3 seconds. What will be the velocity of the car at t equals 3 seconds? Wait, dude, come on, Spaldo. I'm blowing this. Just going to cross this out. At 2 seconds. What will be the velocity at 2 seconds? Another second later. 4 meter per second. What's going to be the velocity after another second? So here it is at t equals 3 seconds now. What's the velocity here going to be? 6 meter per second. All acceleration is, are you guys getting this? All it is the change in velocity per second. Okay? All right, so now on to the last slide for the day. Okay, position versus time graphs. So this pertains to the lab that you're working on right now. So what the lab wants you to do is create a position versus time graph. Okay, so yesterday you went outside, you marked off these positions. 0 meter, 5 meter, 10 meter, 15 meter. You marked those on the ground. And then you had a person standing at each of these positions, except for the 0. So what were these people standing at those, at the 5 meter, 10 meter, and 15 meter? What were they doing? They had the stopwatches, right? And then one of you stood at the beginning, like that, and you started to walk, right? And then this person here got your time at 5 meters. This person here got your time at 10 meters. This person here got your time at 15 meters. So what you're going to do today is you're going to create a graph of position versus time. So see right here? What is X? Position. And then over here is time. Well, let's make this even more clear, just super duper clear. Position. And then down here is time. All right, the thing you need to know about a position versus time graph is that the slope is the velocity of the object. Now, do I want you to memorize this? Should you put this on a flashcard and be like, slope equals velocity, and just commit it to memory? Don't do that. What I want you to do is understand how to figure out what slope is telling you. So all you need to know is what you learned in math class. What is slope equal to? Like, what's the math definition of slope? Rise over run. Okay, so let's look at a segment of this graph. O up to A. So we're gonna look at this part of the graph here. What would the slope of this line be telling us? So kind of don't focus on the numbers right now. Let's focus on the units. What would the unit be for the rise? Here's the rise right here. What's the unit for the rise measured in? Meters. The rise is measured in meters. What's the run measured in? Seconds. We end up getting meters over second, which is what? Velocity. Basically, the numerator, the rise is the delta x, the run is the delta t, which is the definition for velocity. Okay? So what I want you guys to do is calculate. I want you guys to find the velocity at t equals 2.5 seconds, which is going to be actually let's scratch that. Let's just say 3. Make it an easy point. T equals 3 seconds, which is going to be right here. How can we find the velocity at that specific moment in time? Well, how do you find velocity on a position time graph? The velocity is going to be equal to the slope. Now, what's really nice about this part of the graph? There's something really nice about it. It's a constant slope. It's a straight line. Is that what you were going to say? It's a straight line, which means the slope here, 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 at 3 seconds, which is the point I told you to focus on, here. What do all of those points have in common? The same slope. And if the slope is the same, then guess what? The velocity is the same. All of those points that I marked on that first segment there have the same velocity. So what I want you guys to do, take a minute, figure out what the velocity would be at t equals 3 seconds. Okay, so the way you do this, now, A, if it's a straight line, does it matter which 2 points you use? If you're finding the slope of a straight line, I'm going to use this point, I'm going to use the origin and point A, right? Those are 2 easy points. Did you have to use those 2 points? No, you could use any 2 points you want when you're finding the slope of a straight line. So basically we're going rise, which is change of position, over run, which is change of time. This is the slope. So what's the rise? 4. Notice that that's the change of position from 0 meters to 4 meters. That's the change of position. What's the run? 4 seconds. So we get 4 meters over 4 seconds, which gives 1 meter per second. Okay? What's the velocity at 6 seconds? Find velocity at t equals 6 seconds. What's this going to be? Well, what's the slope of this line that I'm circling? What's the slope of that from A to B? 0, because there's no rise, right? The delta x is 0.
I'll be right back.
Okay.
I got 3 8s in here.
Okay. So look, from A to B, what's the rise? 0. And then the run would be 4 seconds, but that still gives 0 meters per second. Okay? Now, what we're going to talk about next week is how you would find the velocity at a point on a curve, like that. See here? What's tricky about this part? It's not constant. It's changing. We'll talk about that next week. Okay?